begin, we add data structures and the built-in libraries. Most programming language problems. So first we're going to cover the basic data types, and then we'll move on to which is necessary if you use Python. I'm using C++ myself. And then we're going to cover a bit why we need data structures and short refresher on data structures learned from other courses. And we're going to look a bit at sorting and searching, then at different representation sets, bit masks. We're going to review some common applications, data structures, then refresh our memory on binary search tree, over a quick modification, powerful. And we'll end by looking at some representation graphs and when they are more useful. So, first of all, the basic data types, bool is true or false, have characters. These are used to represent characters in a string, but in reality it's 8-bit signed integer. Then we have a short, has twice as many bits, int, twice as big as that, and then long, 4-bit. And now generally you'll be using integers, but there are many cases that you need to extend the size of your integer 4 bits, or otherwise you end up overflow errors. Then we have float, double, and long double. And Python, I believe the standard float size is 96 bits, somewhere between the double and the long double of C++. Finally, we have string, essentially just of characters. So an important thing to know is when to use data type, and you need to know the minimum value and maximum value data types can take. If you know your data is going to be integers from 0 to 100, and you are concerned with saving memory, then you should be using either a character or an unsigned character. However, in most cases, we're not really concerned with saving memory, so you can just use an integer. And if you know that your result could exceed the size of integers, so suppose you get two numbers as input, they can both be 2 billion, and you're supposed to add them together, then your result can become 4 billion, larger than the size of an int. So we'll need to use a long there in order to not get an overflow error, where it'll add the two numbers together, but as soon as it passes the maximum value, it'll increment up to the minimum value. Add one value here, get minimum value here. Then we also have the unsigned versions of all of these. They're not very commonly useful, but sometimes you want to use them. In that case, the minimum value is not a negative number, it's 0. And the maximum value is essentially doubled from the signed version. When it comes to floating point numbers, it's mostly concerned position. So when you're solving problems where the result is a floating point number, you are generally asked to output the number with a specific margin of error. So you could be maybe off on the 7th digit, the 8th digit, but sometimes it's even more precise. You can only be off on the 12th digit. And in those cases, you're going to need to use a double or a long double. Just use a float, your answer will not be precise enough, especially if you're doing a lot of intermediate calculations. And I recommend that if you can avoid using floating point numbers, so for example, if you can use fractions, that's good. Because when you do calculations with floating point numbers, there is an error added each time you make any addition or multiplication. The more operations you do, the more error you get. And eventually you'll just end up with an incorrect number. Now, suppose long is not large enough, we accept numbers up to the size of 10 to the power of 100, a 100-digit number. Simple idea to get past this is to just store the integer as a string. But then you might wonder, how do we perform arithmetic? We can't just add the strings together. Then we're just concatenating them. But we essentially just use the algorithms you learned when you were children in elementary school. We add digit by digit, and we maintain the carry. And subtraction is very similar, except then we're borrowing from the more significant digit. Then multiplication and division and modulo is done with long multiplication and long division. If you recall, probably did a method where you found the remainder and the quotient, did division. That's essentially the method. So we're gonna look at a problem called simple. And here it says, yep, yet another trivial problem. You just have to add two integers. Oh, not easy enough. Let's say that they are positive as well. Now it should be trivial, right? Then the input description says that the positive integers are less than 10 to the power of 10,000. So the numbers can be 10,000 digits. And we can see the examples here. So let's implement a class which can handle this. Be the big integer class, handle just addition. Don't need to implement subtraction, multiplication, or okay, so first thing we're gonna do, just gonna read the input.
You're only sharing the Catis screen.
Oh. Now it should be good.
Yep.
We're gonna read the strings. Oh. And then we want implement class called big integer. So I'm going to assume we have that implemented now. Create numbers x, which accept the string a as input. Then y. And we want to calculate big integer set equal to x plus y. Then output that. Okay, so let's create our struct. And we need to store this number as a string. We need a string class. And in the constructor, all we need to do is copy the thing that we're given as here. Say this as. And what we really want to do now is override the plus for the addition operator. So in C++, this is done by calling the operator keyword, then the operator you want, and it needs to accept parameter, a constant, integer, reference. So first thing we want to do here, we want to take copies of the strings, the data, the strings within these big integers. Get a, okay, and to make life easier, we're gonna reverse strings. Then we can go from the lowest significant digit or least significant digit to the most significant digit. If we do not do this, then the indexing will be much more troublesome. We want the least significant digit to be at index 0. Call the reverse function a, and we do the same for b. And to create next string, we're gonna use string. And since we are adding, we need to track the carry. So we add, for example, 7 and 5, get 12. We only want the digit 2, and we want to maintain a carry on. Now for the loop, start at index 0. We want to go up to size of a, but a might be shorter than b, so we also need to check size of b. And also the case where both both of them are equally long, and we're left with a carry. If the carry is not 0, we also want to iterate one more time. So we need a variable for sum, and then we want to add to the sum the value a. If I is less than the size of a, then add character index I minus the character. Okay, and we do the same for b. And then if we have a carry, I want to add that too. Now, check if the sum is less than 10, greater than or equal to 10. If sum is less than 10, then the carry will be 0, and the value of sum in our string stream as the next character. Okay. Otherwise, carry 1 and put value of sum minus 10. So get these. Okay, then after the loop, we want to obtain the string that has been from all these digits. Say string c equal to string stream called the .str function that gets the underlying string. And now since we reversed at the beginning, we have to reverse the result. Then from that string, we can create a big integer, return big integer made from C. Okay. One more thing we need to do. We need to make sure that we can output the big integer. We will write output function here. The big integer, and the output string in integer. By compiling, right? Old compiler, the size fine. Have to do a.size .size. Here. And it's running now. So let's take here. And we get 1379 output. Other input. Try that. And we get the correct output there too. copy the code and it works. Okay, so that was an example of how we can handle larger integers. Now, when we're working with data, we often need to tailor our data structure choice to how we will be working with. So in some cases, we need to be able to query multiple times, and we want some data structure which can query low time complexity. Sometimes we don't need to query at all. We just want to insert. And if you're working with a sequence, maybe we only need to insert at the back. But some cases we need to at the front too, or somewhere in the middle. In other cases, we need to be able to insert and delete. And then in other cases as well, we'd be able to find certain values in the data structure and update them, change them. And this all should affect how we choose our data structure. So often we just need to find better ways to represent the data that we have. For example, in the problem before, we had numbers, we had integers, and the input was given as integers, but we decided to read it in as strings instead and just work with it as strings. And in many problems, we'll be working with graphs. There are many ways to represent them. And the choice of how we represent the graphs is very important. I will cover the details of that at the end of the lecture. So let's cover some of the data structures that you've probably seen before. We have static arrays. These are the default lists in most programming languages. Then we have dynamic arrays. Uh, an array that does not have a fixed size. You can add to it and it'll automatically expand its size. Using Python, this is essentially list Python. Python does not have static arrays, or at least have to specifically import them from some package. We have linked lists, which allow for fast insertion at the front and the back. However, they do not provide random access like static arrays and dynamic arrays do. Then we have stacks, queues, and priority queues. They're all ways of processing our data in some order. Stacks are last in, first out, and they work exactly like a stack in real life. Same with the queues. They work like queues in real life. You queue up, and you're the first to come. You're the first to get served. Priority queues are essentially queues, but have people with different priorities. And if someone has a higher priority, he will skip in front of everyone who has a lower priority than. Then we have sets and maps, which are usually implemented in either hash tables or binary search trees. And since we're using C++, let's cover how each are represented in C++. Static arrays are defined using square brackets. Give the data type and then have the variable name, open square bracket, the size of the array, and bracket. The rest of these are defined within the standard library. You have dynamic arrays, which are the vectors. And note that list is a linked list. Often assume that list is the dynamic array when you start out in C++, but it is the linked list. Don't use list if you want to get random access. Similar functionality as a static array. Then the next ones are just called by the same name. Stack is a stack, a queue is a queue, priority queue is a priority queue, and set is a set, and then maps are called map, and here you have the data type of the key, and then the data type of the value. And in the case of sets and priority queue, you can add another parameter here alongside the data type if you want to define a different ordering. You want the priority queue to not order just by the value of the integers. Maybe you want to make a custom comparator. You are able to do that. And the same in the case of sets. And most cases, you just want to use the standard library implementations. They are almost 100% guaranteed bug-free, and they are also almost 100% guaranteed more efficient than what you would write. It's also convenient because you don't need to write a lot of code, but there are cases where the standard library implementation does not suit our needs exactly. It might come really close, but we need some extra flexibility, or we need to be able to customize our data structure to do some task that is not provided in the standard library. So then you need to implement your own version. Or if you're lucky, the standard library allows you to customize and work with the inner data of the data structure. Now, when it comes to sorting and searching, they're very common operations that probably do in half the programs you write, at least. So sorts are usually defined in the standard library, and you can just use them. There is an exception if you are using Java. The worst case time complexity of arrays.sort in Java is O of n squared. So I would recommend that you do not use that one. However, in most programming languages, the default sort is an n log n sorting algorithm that has been custom built, very efficient in practical cases. So it's very, very good in average cases, but still has a theoretical worst complexity of n log n. And when we're searching in an array, it's important to know whether it is unsorted or sorted. In the case of unsorted arrays, we have to do a linear search. But if it is sorted, we can apply binary search. And I think most programming languages provide some built-in binary search methods. Have lower bound, upper bound, and binary search in C++. In Python, you have the bisect package. And these will do for usually you're just searching through a list. However, binary search can be applied on many things, not just searching a list. So in some cases, you'll need to just write your own binary search, be able to handle the custom case you're working on. So in C++, if you want to sort, you have the sort function, and you have to apply the begin and end iterators sequence. If you want to search through an unsorted array, we have the find function. And searching a sorted array, we use lower bound. Or if there are other functions too, it's upper bound and binary search. They have different outputs. You just have to look at the documentation and use one that suits your need. Okay, now suppose we have a very small number of items, and say n less than or equal to 30, but probably have to be about 26. And let's say that these items we will label them the integers 0 up to n minus 1. And what we can do here is we can represent the set just using a 32-bit integer instead of using that data structure or. And how we do that is that we use the ith bit of the integer as a Boolean value stating whether the item is in the set or not in the set. If the item is in the set, the ith bit's value is 1. If it is not in the set, it's 0. So, for example, with the set 0, 3, and 4, we can define set using a shift operator here. Take the value 1, we shift it by 0 bits, and that will represent the item 0. Same for 3, represent the item 3. And 4, represent the item 4. Then you take the OR of all these, bitwise OR of these, which gives you an integer. In this case, it would be 1, 8, 16. So the number itself would be 25. That will represent. So if you want the empty set using this method, it's just the number 0. And as we saw before, if you want a single element set, just 1 shifted by the value I, or the ith item. If you want all the elements, so the universe set, you shift by the number of items and subtract 1. So if you consider that we have 3 items, for example, shift by 3, and then you get the binary string 1, 0, 0, 0. Subtracting 1 from that will flip all the zeros to 1 and remove the most significant digit. You'll get 1, 1, 1. Okay. If we want to do a union of sets, then as we saw before, we can use bitwise OR operator. For intersection, it's similar. We use bitwise AND. And then for the complement of a set, simply use the bitwise NOT operator, flipping all the bits. However, if you're not utilizing the entire size of the integer, the entire number of bits, we'll have to take the intersection with the universe set. Otherwise, you'll have bits flipped to 1 which are not part of the universe. And we need to be, of course, be able to check if an element is in the set. So how we do that is we simply check if the intersection of x and a single element set, that item, if that is a non-zero number. So you can imagine there's a not equal to 0 here. However, it is necessary. Just gets automatically evaluated as Boolean. Here, if this is true, yes, the element is in the set, otherwise it is. And now why would we ever want to do this instead of just using set of int? This is a very lightweight representation. It saves a lot of memory, for example. If you are low on memory, you might want to do this. It's also nice because all the subsets can be represented by integers in range 0 to 2 to the power n minus 1. And that allows us to very easily iterate through all the subsets, just iterating through a range of integers. And it also lets us use that as an index of an array, which we'll be seeing later when we look at dynamic programming. So what are the applications of arrays and lists? Well, they are way too many. Pretty much every program, right, have arrays, multiples of them. Not necessarily linked lists though. They are rarer, but also very, very common. It usually depends on the insertion requirements. In most cases, we just need to append. So then the dynamic array will simply do. But if you need to prepend as well, then linked list might be the better choice. And here we're going to look at a problem where we require a linked list. Okay, so we're typing a long test with a broken keyboard. The problem with the keyboard is that sometimes the home key or the end key get automatically pressed, and it happens internally, we're not aware of it. And we're just writing our text and did not even turn on our monitor for some reason. And now after we finish typing, we turn on the monitor and we see the text, and we want to know what the text is based on what. So we just get characters here, but there's also the square brackets. This is the indicator that home was pressed, and the indicator that end was. So look here, it says this is A, then home is pressed, page U, end is pressed, text. So that means that, right, this is A, then page U comes front, then text. And here we see home being pressed, home, end, home, home, end. It all happens before we write anything, so it doesn't have any result on the output. So thus of port So the input is a bit different here because we don't get the number of lines. So we need to continue reading until there is no more input. Okay. Need one string to store the content of the line we just read. And then get line on n, word in line, and as a boolean value in the while, return false when there is no more input. Okay, so here we want to use a linked list because we can move to the front and then prepend, or we can append. Want both. And in this problem, we do not require any random access to the characters. We write out the result. The perfect of linked list. We want a list of characters. I will just call it S, essentially a string for us. And then we need to know where we're at. Essentially track where we're at in the list. So obtain an iterator for our positions. And we start at the beginning. Note that this iterator here as end, it is the position after the last element. Okay, and then we just want to read through each character the line and handle the different cases. We have the two special cases of home and end button. So if we look through the size of the line, and we check character is home key, now in this case we want to go to the start of the linked list. So we will say it equal s.begin. Now if the end key was instead pressed, we want to go to the end. It is equal s.end. And otherwise we just want to insert the character. So say s.insert at the iterator's position, value line I. Right. Yes, and then we need to output string. So we use the iterator we had, set it to start, and while we're not at the end, iterate and just output the value at the iterator's. Let's try. In the first case is a Beiju text. get a to the text. That works. However, one thing. I did. What I'm gonna do is I'm gonna input files. And I forgot to write an end, that the output doesn't get mangled together. And then we run it, and our input file. Then we get the correct output. Okay, this was a problem on UVA, so we cannot submit test. The correct method to solve the problem. If you use a dynamic array here, you get time limit exceeded. Okay. Next step are stacks. So what are the applications of that? Of course, just the standard last in, first out order processing. Then there is the simulation of recursion. Recursion is very convenient for writing code, but it does have some drawbacks. There is the overhead of each call to the function. So in general, recursion is lower. If you want to optimize your code, you may want to write it iteratively, but simulate the recursion use a stack so that you don't have to change your logic to. One of the most common applications of a stack is the depth first search in a graph. Then you can of course also use it to reverse a sequence, but have built-in functions for that. Then there's a very common problem in science and embedded programming too, or at least some variation of it, is when you have brackets that you want to match. Sometimes just a single type of brackets, but in other cases you have a mix of. For example, when the code you write, you usually have a mix of brackets that need to match. You stack to determine if they are matching. And there are a ton of more applications, of course. And in queues, we of course have the first in and first out. And then, similarly to the stacks, we have an application in graphs. In this case, it's the breadth first search. And that one will give us not just some path, give us shortest path graph. In priority queues, of course, again, we have a very common application in graphs. There is the shortest path in a weighted graph. And this is, of course, Dijkstra's algorithm, uses a priority queue. Then many greedy algorithms also make use of a priority queue. simply for a selection of an item. The priority queue is built up and it has some character to determine which is the best item, and then you just pop off the front. How a lot of greedy algorithms work. Then we have sets. The most common use of sets is just to make sure that the items we're tracking are distinct. And then of course there is a case where we just want to be able to quickly check whether we have item, seen it before. And other cases we can handle if it is implemented as a binary search. Now, many languages it's implemented as a hash table. If it is a binary search tree, we can find the successor of an element or the predecessor. Successor is the smallest element that is greater than the element that we provide, and the predecessor is the largest element smaller. So essentially, if you were to look at the set as a sorted list, you find the position of the item you're looking for, and then you look to either the left or right, depending on whether you're looking for the successor or the predecessor. We can also count the number of elements in our set which are less than a given element. And we can extend that and count the number of elements that are between two given elements. Get these number in a certain range. And then if we wanted to find the eighth largest element, we could also do that. Then there are maps which are implemented the same way as sets, but they also have another value associated with them. So usually we're just using this to create a map like function mapping. So have some key and we want it to map to a value. For example, maybe an encoding or a decoding function. We can use them as a frequency table. So we're counting the number of times each character appears in the string. We're doing some linguistic analysis in our program. Then I mentioned dynamic programming earlier. The maps are very commonly used as the memory in a dynamic programming. So the basic idea in dynamic programming is that you store the result of the function call memory, and then you can just access it. And maps are useful there when the input of the function is not an integer, for example, a string. Then the input of the function is the key, and the value is the result of the function. Now, talked a little bit earlier about how sometimes the standard library does not suit our needs entirely, and we need to customize it. And often we cannot just do this directly to the data structures in the standard library. We need to write our own implementation of the data structure and then make the changes required. So, for example, binary search trees are data type set plus, but that does not provide all of the operations I mentioned earlier. So let's look at how we can augment binary search. So suppose we have a binary search tree and we want to count the number of elements that are less than some integer x, right? We also want to be able to find the kth smallest element. Now, we could, of course, just iterate through the entire set, essentially putting the values in sorted order. So if we were to start at the 5 here, and the binary search tree order of size, then we would have an O of n algorithm for both of these methods. But that's pretty slow. We want it to be logarithmic or faster. So instead of just storing the value, we will store another number in each node, which is simply the size of the subtree. So if we look at this node here, have the value 15, and the size of the subtree is 5, because we have the left subtree is of size 2, the right subtree is size 2, and then we have this node connecting, have 5. And we can maintain this information as we insert and delete elements without increasing the time complexity of those operations. So let's count the number of elements are less than 38. So we're gonna basically do a search, a binary search tree, the same way we do usually. And we're gonna use the subtree size to count the number. So how we do that is, suppose we're at this node here, have the number 38, and we're looking at that, but here we have the number 33. So we know for sure that 38 is larger than everything in the left subtree, and it's larger than the value here. So we know we can add the size of the left subtree, 5, and 1 extra count. Then move on to this one. But in the case we're moving left, then we don't add anything, because our value is smaller than everything here and the right subtree. 38 is smaller than 47, and it's smaller than everything on the right of 47. Okay, so if we were to do this, we would first go right, we add 5, and we add also for this node here. We move here, go left, and add nothing. And then we would go right here because we are at 38. And we add the size of the left subtree here. Now, since it's strictly less than 38, we not add this node. You could also write this function with just less than or equal. Just depends on what you're doing. And the time complexity of this is, worst case, the height of the binary search tree, which if we have a self-balancing binary search tree, like a red-black tree, it'll be big O of log n. Now, similarly, can devise an algorithm to find the kth smallest element. So we're on this vertex here, and the size of its left subtree is of size m. Then we know that if k is less than or equal to m, it's gonna be in the smallest, or it's gonna be in the left subtree. If it is equal to m plus 1, then it is the node we are currently at. There are 5 values in the left subtree, k is 6, then okay. Otherwise, k is greater than m plus 1, we want to look in the right subtree. But we have to offset k now, because we no longer have the left subtree here and the node we just came from. So we have to subtract from k the size of the left subtree and then 1 extra. Okay, so if we take an example where k equals 11, here we first have the case k is greater than m plus 1. M is 5, so m plus 1 is 6. So we move to the right, and now we update k. K is now 5. Okay? And we see that the size of the left subtree is 5 here. So 5 is less than or equal to 5. We look in the left subtree. We just move to the left, and we're still looking for 5. Here we have m is equal to 3. 5 is greater than 4, so we move to the right, and we subtract 4. And here we have no left subtree, so the size is 0. So that means that, when we moved here, we need to update k again. Subtract m plus 1, which was 4. So we have k equals 1 now. And now the size of the left subtree is 0. And then k is equal to m plus 1, and we have found our value. And this is the final topic of today's lecture, is the representation of graphs. There are many different types of graphs. We have, especially with edges, we have directed versus undirected. We're working with directed, but undirected are also quite common. Have weighted graphs versus unweighted graphs. Have simple and non-simple, and what that usually that we allow for self loops, possibly, or we could allow for multiple edges between the same pairs of nodes. There are special graphs like trees, represent in different ways. There are function graphs. There are whole wide number of different types of graphs which could represent specifically based on their structure to optimize our code. But in general, we have 3 methods to represent graphs. They are the adjacency list, adjacency matrix, edge list. And the most common one we'll be using is adjacency list. It is usually the most practical one. And in the adjacency list, we store for each node uh, which nodes we can reach from it. Here we have an undirected graph. So if we look at the node 0, we have edges going to 1 and to 2. That means that the list at index 0 is going to contain 1 and 2. 1, similarly, we have edges to 0 and 2. So the list at index 1 has the value 0 and 2. 2 has 3 edges, 0, 1, and 3. So it is larger than the other ones and has the value 0, 1, and 3. and 3 can only reach 2, so the list contains the value 2. And here is how we would create this graph. So we have an array of integer vectors. Call it ADJ, short for adjacency. And for vertex 0, we push back the values 1 and 2. Vertex 1, we push back 0, 2. For vertex 2, we push back 0, 1, and 3. And for vertex 3, we push back 2. Now, the adjacency matrix is a bit different. Essentially, we make a table, a Boolean table, which states whether two vertices are connected. See here that this is a symmetric array by the diagonal here, and the reason is because the graph here is undirected. So what it means for this value to be 1 is that we're in the first row and the third column, so it means that we can reach vertex 3 from vertex 1. There is an edge going from vertex 1 to vertex 3. And because the graph is undirected, that of course in turn means that there is an edge from 3, 1. And the diagonal here is 0 because there's never an edge going from a vertex to itself. Simple graph, there are no self-loops. Here we see how we could define in plus. We make the two-dimensional Boolean array here, and then for each pair of nodes we want to connect, set the value to true. Final common representation is the edge list, and it is used in a minimum spanning tree algorithm, which you're probably familiar with. Here we have essentially just pairs representing the edges. So we have 4 edges in this graph. We have an edge from 0 to 1, so we have the pair 0, 1. We also have an edge from 0 to 2, 1 to 2, 2 to 3. And note that we do not put in 0, 1 and also 1, 0 undirected graph. If it were a directed graph and we had edges going from 0 to 1 and 1 to 0, then we would have both of them. So here we define a vector of pairs of vectors, call it edges, and to add to this we need to put back the make pair function here, making the pair of 0 and 1, which will return a pair type here for us, a convenient. Okay, so if we look at the time complexities, we can see when each of these is useful. So the maybe most notable thing to look at is that in both cases of adding a vertex and adding an edge, the adjacency list and the edge list provide constant time operations for that. But the adjacency matrix cannot add a vertex quickly. It can add an edge, but not a vertex. Then you need to resize the entire array. So immediately, if you know that you might need to add a vertex later on, you know that adjacency matrix is not the correct, probably. Same with removing. So if you need to add and remove edges constantly, then maybe adjacency matrix is correct choice because it has constant time operations for 2. But in general, the adjacency list is the correct choice. The main exception I can think of is in a specific problem where you want to count the number of paths from A to B, from two vertices in the graph. The adjacency matrix is very useful for that, since you can count the number of paths from A to B which are of length k. It's very useful in that case because you can use the matrix and raise it to the power of k, and it'll give you the number of paths. That's a very specific case. And edge list, usually we just use it for the minimum spanning tree algorithm. I honestly can't even remember the last time I used a competitive programming setting, except in the exact problem I described here, and in the minimum spanning tree algorithm for edge list. So generally you are using the adjacency. But you need to be aware of these time complexities. So if you do end up in a situation where the adjacency list is not optimal, you're able to switch to other representations. Okay, so the last problem we should look at is phone list. So in this problem, we are given a list of phone numbers and we want to determine if it is consistent, in the sense that no number is the prefix of another. Case in our phone number system in real life. Here we have emergency 911. Bob has a number starting with 911. So in this case, it's not possible to call Bob because you'd be directed to the emergency line. Okay, and the inputs are P for a number of test cases. Test case has a number N, which is 1000. And then there are N lines, phone numbers, phone number digits. So here we need to be able to check for each prefix whether we have seen it before in our list. Let's look at how we do that. Okay, so first we need to read the number of test cases. And I'm gonna be using a macro I have defined, wrap macro. So it's essentially just a for loop, t going from 0 to the value of ts. And here we read the integer n. We need to store all our strings, so we're gonna need an vector strings. I'm gonna R for array. And then we also need to track all the prefixes. That. Now a set of strings, call it capital S. Iterate and all phone numbers. Feed in. And we want to insert. So we have sorted in our list and we have that. And then we want to check if this isn't list. So let's first assume that list is consistent. And as soon as we find something telling us otherwise, that consistent false. Assume it is true. Now what we want to do is we want to iterate through all prefixes of each string. So first of all, iterate through n. And within here, we need to iterate through length. So for L equals 1. Don't want 0 because we want to 1 digit. While L is less than the size of Ri. Right? And here, the first thing we need to do is take the prefix as a substring. Let's define the string substring starting at index 0 with length L. If we are able to find this prefix in our set, then we know that the list is not consistent. So if S dot find of not equal to S dot end, so we get some iterator an item in the set. Then consistent is false. Break from this loop. And if after this loop found that false, if not, break from the outer loop. Recap, we start by reading in all the data and inserting each phone number into a set. That will allow us to quickly look up if the phone number, if we have seen this phone number. Then we iterate through all the phone numbers. We try all prefixes and check if the prefix is in our set. Essentially checking if there is a prefix of this phone number, which we have in this list of phone numbers we have. If that is the case, it is an incorrect set considered false when we find something like that, and then break out of the loop. And finally, we need to output the result. So if consistent, the output yes, and otherwise we output no. Okay, and that's only one sample. Copy it, file, .1. And pass that in as the input. We obtain no and then yes, which is correct. Let's try submitting this. And it is. Now you'll note that it took us 0.58 seconds, like this. If the constraints were any higher, different data structure than a set, which we will cover later days, specifically made for strings. Can see often stats page passes. Here you can see there are people running in 0.6 seconds, much faster than this minute. And I know many people, they like to optimize their code, try to get to this leaderboard. So don't worry, I will be method with even more speed. Okay, that's it today. Any questions? Kent?
Yeah, I have one. So you said that big integers, we shouldn't worry about that in Python.
Yeah.
So we can
Well,
add any number and they use that underneath or what?
yeah, so the default data type in Python is big integer. There is one thing you need to worry about. So I talked about the different operations. We have addition, subtraction, multiplication, and division and remainder. So suppose you're working with very large numbers, similar to what was in the problem, maybe 10,000 digits. Then division will become really slow, and remainder, because that's the same operation, essentially. Because the time complexity of division in Python is n squared, where n is the number of digits or bits. Yeah, I think it's bits. However, in for example Java, big integer class has a better algorithm with I think big O of n times the square root of n. So it's really only there you need to be concerned about it. Only if you're doing division Python with very, very large numbers. Okay, any more questions?
Perhaps just one more. Should we implement the augmented binary search tree just to have it, or should we just, think about it if we get a problem that has something like that in mind?
I mean, it's good practice to implement, but if you, it's gonna be maybe more tricky if you want to make it self-balancing.
Exactly.
Don't think you necessarily need to implement it. It's just it's more important that you are aware of the possibilities that you can do.
Mm-hmm.
So that in the case you encounter a problem where this is one of the tasks you must achieve, it, that you are aware that you could use binary search to solve this. And there is I mean there are implementations online which once you're done with this course you are of course free to use uh, whenever you feel like. So don't necessarily need to implement by yourself, but definitely good practice.
All right.